Okay, so this is chapter 7, input output. This is the last major component that we're going through in terms of the overall architecture. This is a really long set of slides, so I'm breaking this up into several different parts, and this is the first part where we'll have an overview and the different type of devices and different types of structures that we can use for controlling I/O. So let's begin. And we've looked at the processor, which is the arithmetic logic unit combined with the control unit. We've also spent quite a bit of time looking at memory, both internal and external, cache memory, external memory, disk drives, etc. Even down to the level of the register. The other major component in the von Neumann architecture is input-output in the form of a set of I/O modules. And here we can see Katherine Johnson from NASA holding some output from that IBM machine there. I'm a big fan of history, so take a look back at the things that she accomplished if you are interested in the history of computers as well. So to deal with the input and output, we have input-output modules or I/O modules, and they have two major functions. One is to interface to the processor memory via the central bus or a switch. And then to interface to one or more peripheral devices by tailored data links. So here we can see that it connects to the bus on the top, and it connects to the peripheral devices at the bottom. There are a wide variety of peripherals with a whole bunch of different ways of operating. I/O is the most non-standard portion of the computer architecture. The data transfer rate of peripherals is often much slower than that of memory to the processor. On the other hand, there are some peripherals that are faster than the transfer of memory to the processor. Peripherals often use different data formats and word links. So that's why we have the I/O module connecting between the device itself and the bus. So that's why it acts as an intermediary. So external devices, there's our famous PC load letter, and here's a bunch of old hardware that you may or may not remember, but external devices provide a way of exchanging data between the external environment and the computer. They're attached to the computer by a link to the input-output module, and that's used to exchange control status and data between the I/O module and the external device. A peripheral device is an external device connected to an I/O module. And there are three categories of external devices. One is human readable, which are suitable for communicating with us, the computer users. These are things like video display terminals, monitors, printers, etc. Then there are machine readable, which are suitable for communicating with other computing equipment, such as magnetic disk or tape systems, sensors, or actuators that you may attach to the computer. And then there are communication devices suitable for communicating with remote devices, such as a terminal, machine readable device, or another computer. And that's a modem, in case anyone didn't recognize it. That's how we connected to the large mainframe computers back in the 1970s. So the external device itself will have several different modules. It'll have control logic that controls the device's operation in response to the input-output module, a buffer, and a transducer. The transducer converts data from electrical to other forms of energy, and that has data going to and from the environment going into the transducer. So the keyboard monitor is the most common means of communication with the user. The user provides input through the keyboard, and the monitor displays data provided by the computer. The basic unit of exchange is generally the character, and associated with each character is a code. Each character in this code is represented by a unique 7-bit binary code, and there are 128 different characters that can be represented. There are two types. There are printable ones that can be printed on paper or screen, or control characters, which control how the output is displayed. For example, CRLF, which is carriage return line feed, or there are different communication protocols such as start and stop transmission that can be control characters as well. You can see those if you look at an ASCII table. So when the user depresses a key, it generates an electrical signal that is interpreted by the transducer in the keyboard and translated into a bit pattern and then corresponding international reference alphabet code. The bit pattern is transmitted to the I/O module in the computer, and on output, the international reference alphabet code is transmitted to the external device from the I/O module. And then the transducer within that device interprets the code and sends the required electrical signals to the output device, either to display the indicated character or to perform the requested control function. Disk drives, another external input-output device. Even though we treated them as memory, we can also think of them as input and output devices, and they contain electronics for exchanging data, control, and status signals with the I/O module. In a fixed head disk, the transducer is capable of converting between the magnetic patterns on the moving disk surface and bits in the device's buffer. Moving disk head also needs to be able to cause the arm to move radially in and out across the disk surface. So I/O modules are what control the input and output, and they have several major functions. One is control and timing, communicating with the processor, communicating with the device itself. So they act as an intermediary between the processor and the device, buffering data to balance device and memory speeds, and detecting and reporting transmission errors. So in terms of processor communication, they act to do decoding for commands. So the I/O module accepts commands from the processor that are typically sending signals on the control bus and then decodes what those mean. Data are exchanged between the processor and the I/O module over the data bus. They can also do status reporting. And again, peripherals are slow. Things like printing takes a long time. So you need to know the status of the I/O module, and it can tell you, hey, I'm busy or I'm ready to receive more requests. And then address recognition. Each I/O device has an address. The I/O module needs to recognize one unique address for each peripheral control. So, you know, the mouse will have an address, the keyboard will have an address, the printer will have an address, and the I/O module needs to recognize each one of those addresses. Other tasks, the I/O module needs to perform device communication, give commands, get status information and data from the devices, needs to buffer data that come in from main memory that are sent to an I/O module rapidly, and it needs to perform error detection. So here's the overall I/O module structure. We have the interface to the system bus over on the left, the interface to the external device on the right. There's the I/O logic that has the address lines and control lines, the external device interface logic, which allows us to send and receive data, get the status of the external device, and control the external device. So there are three different techniques for I/O operations, and one of these is programmed I/O. We're going to see that in section 7.3. Here, the data are exchanged between the processor and the I/O module. The processor executes a program that gives it direct control of the I/O operation. When the processor issues a command, it needs to wait until the I/O operation is complete. Sometimes that can be a while. The processor is faster than the I/O module, then that kind of is wasteful of processor time, but again, this is a fairly simple technique. Interrupt-driven I/O, we've already seen how interrupts can be added into the fetch, decode, and execute command cycle. Here, the processor will issue an I/O command, continue to execute other instructions, and it gets interrupted by the I/O module when the I/O module has completed its work. So it kind of offloads the input and output onto the I/O module. And then there's direct memory access. The I/O module and main memory exchange data without the processor being involved whatsoever. So here's a breakdown of the three major techniques and how they work. So programmed I/O, that's the memory transfer through the processor. It has no interrupts. Interrupt-driven I/O is, again, I/O to memory transfer that goes through the processor, but it uses interrupt. And then if you do direct I/O to memory without the use of the processor, that's direct memory access. And we'll see each one of these three in the coming presentations. Thanks so much for your time.